Hi everyone, in this video we're going to learn about the kinetic molecular theory, and we're going to dive into its applications, like the root mean square velocity and Graham's law of effusion. The kinetic molecular theory is the simplest model that we have to understand gases. In this model, we view gases as a collection of particles that are in constant motion, and these particles are moving in a straight line until they collide with each other or with the walls of the container. Now, in order to use the kinetic molecular theory as a model for gases, there had to be a few assumptions that were made. The first is that the size of a gas particle is negligible. So really what we're saying is that the gas particles have no volume. Now this might seem weird, like, doesn't the particle have to take up some space? But maybe this will help you. If you have a sample of argon gas and it's at STP conditions, about 99.9% of that volume that the gas is taking up is empty space, because only about 0.01% of the volume is actual argon atoms. That's just how small and far apart these gas particles are. So when you think about gas particles from this perspective, it's not such a far stretch to assume that the size of the gas particle is negligible. The second assumption is that all of the particles in a system have the same average kinetic energy at a given temperature. Kinetic energy is the energy associated with the gas particle's motion. And what this assumption is saying is that if you got a sample of gas particles and they're all moving around, so they've got kinetic energy, no matter what type of gas particle it is, they will all have the same average kinetic energy. And that's because they're at the same temperature. But just to be extra clear, just because all of the particles have the same average kinetic energy does not mean that they are all moving with the same velocity. The lighter particles will move faster, and the heavier particles will move slower. And this makes sense. In order for a lighter particle to have the same kinetic energy as a heavier particle, it has to go faster. Same goes for the heavier particles. In order for them to have the same kinetic energy as the lighter particles, it has to move slower. And now let's look at the third and final assumption, which is that all of the collisions that these particles make are perfectly elastic. What that means is that there's no loss of energy when the particles collide with each other or collide with the walls of the container. And so that's the kinetic molecular theory. And we use this to try and understand the behaviors of gases. But what's really important for you is understanding two of the applications of the kinetic molecular theory. The first is the root mean square velocity. The kinetic molecular theory was used to derive this equation for the root mean square velocity. And if you're thinking to yourself, what the heck does root mean square velocity even mean? Well, the way I like to think about it is it's kind of like the average velocity. It's not exactly the average velocity, but conceptually they're very similar. Now let's take a look at this equation. I want to hone in on this fancy m. This variable is just the molecular weight of the gas, but very importantly, it has to be in kilograms per mole. Usually molecular weight is in grams per mole, so you always have to convert it to kilograms per mole. And now because the molecular weight is in the denominator, this tells us that the root mean square velocity and molecular weight are inversely proportional. That means lighter gases will have a larger root mean square velocity. But we already knew this. Lighter gases move faster. On the other hand, heavier gases will have a smaller root mean square velocity. But again, we knew this. Heavier gases move slower. And now before jumping into a practice problem, let's look at the other variables. We've got R, which is our gas constant, and for this equation you have to use an R value of 8.3145 joules per mole per Kelvin. And then we have T for temperature, and your temperature has to be in kelvins. And when you do your calculations, the root mean square velocity will have units of meters per second. So it has the same units as velocity. And now here's a quick quiz for you. If we're looking at oxygen gas and hydrogen gas, which one will have the larger root mean square velocity? The answer is hydrogen gas, because it's lighter, so it will move faster. Now let's jump into a quick question to practice using this equation. Alright, so in this question, we're asked to calculate the root mean square velocity of nitrogen gas at 25 degrees Celsius. The first thing we're going to do is write out our equation for the root mean square velocity. So we have the square root of 3RT divided by m. Now R is the gas constant, and that's 8.3145 joules per mole per Kelvin. T is the temperature. They told us it's 25 degrees Celsius, but we know it has to be converted to kelvins. All we need to do is add 273.15 to our 25 degrees Celsius. And that gets us a temperature of 298.15 kelvins. Next, we need to convert our molecular weight from grams per mole to kilograms per mole. All we need to do is take our molecular weight, which is 28.02 grams per mole, and convert the grams to kilograms. And that gets us 0.028 kilograms per mole. And now we have everything we need to solve for the root mean square velocity. All I need to do is plug in my values, and then when we do the math, you can see that the root mean square velocity for nitrogen gas at 25 degrees Celsius is about 515 meters per second. Just take a minute to think about that. The average velocity of nitrogen gas at room temperature is about 515 meters per second. That's about 1,854 kilometers per hour. That's how fast these gas particles are moving. The second application of the kinetic molecular theory is Graham's law of effusion. Now, what is effusion? Well, it's the process by which a gas escapes from a container into a vacuum through a small hole. So you can imagine if we've got this container and it's got two sides. One side is full of gas and the other is just an empty vacuum. Now there's a wall separating these two sides, but it has a small hole in it, which means the gas particles can go through the hole and escape into the vacuum. Effusion is the rate at which those gas particles are escaping through the hole. And now that we understand effusion, let's take a look at Graham's law of effusion. This equation was derived from the kinetic molecular theory, and it's used to compare the rates of effusion for two types of gases. So we would have gas A and gas B. Gas A would have its own rate of effusion, and it would have its own molecular weight. Gas B would have its own rate of effusion, and it would have its own molecular weight. And that molecular weight can be in grams per mole. And now let's jump right into a question to practice using this equation. Alright, in this question we are told that an unknown gas effuses at a rate that's 1.32 times that of nitrogen gas. And we are asked to determine the molecular weight of the unknown gas. Now the first thing I always do is write out my equation. So this is the generic equation. But I find the trickiest thing in these questions is putting the right variables in the right place. So we are comparing the unknown gas to nitrogen gas. That means when we're setting up the left side of this equation, we want to put the rate of the unknown gas as the numerator and the rate of nitrogen gas as the denominator. And I know this because we're comparing the unknown gas to the nitrogen gas. But be careful, because on the right side of the equation, you will put the molecular weight of nitrogen gas as the numerator and the molecular weight of the unknown gas as the denominator. Now the next thing we want to do is we want to start filling in some of our values. But we weren't told what the rate of the unknown gas is or what the rate of the nitrogen gas is. We were just told that the unknown gas effuses at a rate of 1.32 times that of nitrogen gas. What that means is that this whole term is equal to 1.32. And now let's look at the right side of this equation. We know the molecular weight of nitrogen gas, that's 28.02 grams per mole, and we're solving for the molecular weight of the unknown gas. So now all we need to do is rearrange this equation so that we can isolate for the molecular weight of the unknown gas. And when we do the math, we can see that the molecular weight of the unknown gas is about 16.08 grams per mole. And here's a little quiz question for you. What gas has a molecular weight of about 16 grams per mole? If you guessed oxygen gas, great job. And so that's how you use Graham's law of effusion. And with that, that's the end of this lesson on the kinetic molecular theory and its applications.